So, we have seen second order linear differential equation, ordinary differential equation. We have seen how that can be converted to a system of coupled two equations, first order linear equations. So, we have seen how it is done. We will study today the properties of the second order linear ordinary differential equation. So, we start with the equation. So, let second order equation is second order linear ODE. This is a naught x y double dash plus a1 x y dash plus a2 x y equal to some bx. So, x belongs to the domain some interval which is in the real line. So, I can be either a finite interval or semi infinite interval. So, I can be equal to a b the open interval, or a to infinity or minus infinity to some a and some minus infinity infinity. It is a full R. Okay. So, this is how I can be. Since we have seen that whenever you have this one, the highest coefficient of the highest derivative should not be 0. So, those are the x values when a naught f x should not be 0. So, we have seen that a naught f x should not be 0. That means the domain should be having all the values for which a naught of x is non-zero. Because this is non-zero, I can rewrite. So, a naught plus a1 by a naught into y dash plus a2 by a naught into y equal to b by a naught, bx by a naught. So, where a naught, a1, a2, b, these are all given functions. So, this is equivalent to saying y double dash plus px y dash plus qxy equal to some, so you can say Rx, this is Rx. Rx is b by a naught. So, x belongs to I. So, what are the properties we have? Properties of the solutions of a second order linear ODE, which is homogeneous when R equal to 0. So, the properties we will find some properties of solutions of homogeneous equation y double dash plus px y dash plus qx y equal to 0. So, I consider only homogeneous equation, that means the right hand side Rx is 0. So, such an equation, so we look at the solutions. Suppose if I give you one, property 1 is if I give you two solutions, y1 and y2 are two solutions of this equation, then its combination, linear combination is also a solution. So, let me write what it exactly it is. If I give you two solutions y1x and y2x are two solutions, then linear combination y1 c1 y1 plus c2 y2 is also a solution, where c1 and c2 are constants. c1 c2 are constants. So, how do we see this? You know that y1 is a solution. So, you are given y1 and y2 are two solutions. So, you substitute. So, you see that y1 double dash plus p x y1 dash plus qx y1 equal to 0 and y2 double dash plus px y2 dash plus qx y2 equal to 0. Okay. Now, we want to see c1 y1 plus c2 y2 double dash, substitute just simply c1 y1 plus c2 y2 into the equation, just verify whether it is 0 or not. So, left hand side I am just substituting, you have a px c1 y1 plus c2 y2 dash plus qx c1 y1 plus c2 y2 equal to, what is it? This is actually equal to, you can rewrite c1, because it is a constant. If I differentiate this will be y1 double dash plus c2 y2 double dash plus px C1 y1 double dash y1 dash plus Px C2 y2 dash plus q C1 qx y1 plus C1 C2 qx y2. This I can write, take the coefficient of C1, coefficient of C2, what you have exactly, y1 double dash plus Px y1 dash plus Qx y1, and here y2 double dash plus Px y2 dash plus Qx y2, and we know that this is 0 because these are known equations, these are known solutions. Y1 and y2 are solutions of the equation, so this has to be 0, this has to be 0. Okay. So that makes it completely 0. So that implies this one, if I substitute in the place of y, is also satisfying the equation. Okay. So that implies this is also a solution. Okay. So this is how you show that. So if I give you two solutions, the linear combination of, this is called the linear combination, C1 y1 plus C2 y2 is a linear combination. This is the linear combination of two solutions y1 and y2, is also a solution. So before I proceed to give you some other properties, I define what is called independence. If I give you two functions, if y1x and y2x, they are not solutions of the equation, y1 and y2x are two functions defined on I. That means x belongs to I. I can be any interval, open interval, and they are, and let us say y1 of x divided by y2 of x. You divide it 1 over it. If this is equal to not a constant, if this is not equal to constant, then we say that y1 and y2 are two linearly independent functions. So that means two functions are linearly dependent if they are y1 by y2 equal to constant. That means one is constant multiple of other. That means you take two functions like this, y1 is this, y2 is this. If they are exactly parallel, wherever defined over I is from between this and this, if they are parallel, they are linearly dependent. If they are not parallel, say let us say like this and then goes parallelly, still they are linearly independent, because y1 and y2 is not a constant. Here it is constant up to here, wherever up to here is constant, but here from here to here it is varying, it is not a function of, it is just function of x. At this point this divided by this is different. Okay. So at this point you have this divided by this is your y1, this is your y2, y1 by y2, every time you pick up the value here, so you have a different value, so it is not a constant. Okay. So we will say otherwise they are dependent, linearly dependent functions. Okay. Like this a1x1, a1x plus b1y equal to c1, and then a2x plus b2y equal to c2. Suppose you have this system of linear equations. When do you have a solution exists for this linear equations? You have solution exists, solution is, unique solution is possible if the determinant, what is the determinant? If I can rewrite equivalently this system of equations, you can write Ax equal to some C, these are this is the matrix, this is vector, and this is matrix 2 by 2, 2 by 1, finally 2 by 1. So what is A? A1 B1, A2 B2. X is xy equal to C is C1 and C2. if the determinant of this matrix mod A, okay, so determinant of A, that is A1 B2 minus A2 B1, if this is non-zero, I know that I can invert the equations. I can invert this matrix to get the xy. Xy is nothing but A inverse of C. Okay, this is all you get. So this is the condition. So, and also another way of saying is, suppose if I can find some non-zero, if x non-zero, a matrix, it's a vector which is non-zero such that A x equal to 0. Okay. So that means if I choose my C1 and C2 0, 0, 0, then I will have a unique solution when A is having inverse, that is 0. Okay. If this is non-zero, so that means if I have a system for which you have a non-zero solution, then I must have determinant of A should be equal to 0. Okay. If this is non-zero, suppose this is non-zero, then I can invert it, I will get only x equal to 0, but it is given that it is x non-zero. Okay. So before I give you property number 2, so I will explain some existence and uniqueness theorem for the linear second order ODE. So let me write it as a theorem. So your equation is y double dash plus px plus px y dash plus qxy. Let us take 0, need not be, so we can take in fx, right hand side, non-homogeneous equation where x belongs to I is open interval or full real line. So let be the equation, be the ODE, be the linear ODE with px, qx and fx or continuous functions. In I. Suppose px, qx and fx, these functions are given, and if they are continuous functions, and what you have is you have a second order linear non-homogeneous equation, and then if once you see these coefficients px, qx and right hand side fx, if they are continuous in I, so you have a unique solution. This equation will have a unique solution. Okay, unique solution if you provide initial conditions. So you provide the initial conditions, that is y at x naught. X naught belongs to I. Okay, so x naught is given as y naught, y dash at x naught equal to y1. Okay, so where x naught belongs to I. These with and initial values. So function value, unknown function value, and its derivative is given at some point at x naught. Then this the initial value problem. So that consists of this and these two. We'll have then the initial value problem. I'll write this initial value problem. That means this one and this one together. So IVP, we can call this IVP, has a unique solution. Unique solution yx for every x in I. So we can say this one. Okay. So this is actually so we can somehow proof is beyond the scope of this course. What we do is we'll just give you the justification why this theorem is true. Okay. So basically the proof is by converting this initial value problem, this and this, you convert this as a first order system, that as we have done earlier. So if you write some justification, we can give justification of the proof. So y double dash plus px y dash plus qxy equal to fx and you have these initial values y1. So, this is actually, you can put it as the equivalent form as ddx of first order system of equations, or first order equation for a vector valued function. So, for a vector y at x, y dash at x. So, this is your vector. So, for this, if you take the derivatives, what you get is the matrix 0 1, and this will be your y of x. Okay. So, this is your y of x and y dash of x, and then you have minus qx minus px. This is a matrix. If you actually do this, y dash, first element is derivative. So, y dash equal to, if you actually do take this element, this multiplication, you will get y dash equal to y dash. So, the right hand side should be 0. And what happens here, the second element y double dash, that is coming from this equation, that is fx. So, I should have fx here. Okay. I have fx, and then minus pxy dash, and minus qxy. So, that is how you get this system. And what is the initial values? Y at x naught, y dash at x naught. So, this vector at x naught is already known. So, that is given as y naught y1, okay, where y naught y1 are the real numbers. So, this is how you see, if you view the second order system as like this. So, if you see this as a vector valued function yx and y dash of x, okay. So, this belongs to R2, okay. And what is your right hand side? So, what is your right hand side? ddx of this is the left hand side, remaining is the, this is what is the right hand side, okay. This is your right hand side. The right hand side is actually function of some function of, let me write this as some function of this, if you call this x, okay. So, fx with small x, okay, as a function of x. So, that is enough. So, fx is ax plus b, that is a, if I call this this vector as x of x plus b. This is a vector, this is a vector, this is a matrix, A is a matrix, okay. So, this is how you have with the initial value. So, first of all, this is what it is. So, if this is a function from x is here in R2 to, where is it going? So, this is from 2 by 2 multiplying with 2 by 1. So, that is going to be 2 by 1, okay. So, 2 by 1 vector, 2 by 1 vectors together it is 2 by 1 vector. So, it is basically again in R2. So, what is the derivative f dash? Okay, if I want df by dx, this is actually, you can view this as a scalar equation, and its derivative is actually the matrix itself. It is an operator, okay. So, this if you do not know, this is from R2 to R2 is any derivative. So, derivative of f with respect to the vector is actually, think of this as ax plus b. So, its derivative is simply a. So, you have, this is an operator. So, this is our derivative is an operator here, because it is from R2 to R2, okay. So, if this is the norm, so that means what is the modulus? What is, where is a? Is an operator, a is 4 elements, this is in R4. So, modulus of that is actually square root of squares of sum of the squares of all the 4 elements in the matrix, okay. If that is finite for every x in I, that is true, because 0 is continuous function, q is continuous function, p is continuous function, and they are defined on I. Square of this p square, q square, they are all continuous functions. On I they are finite. So, you can say that this is finite. So, if this is the sufficient condition, okay, because you have chosen them as a continuous function, they are continuous functions, okay, and these are all continuous functions. So, this condition is satisfied. So, if this is satisfied, then you have the system dx by dx, okay, x of x equal to f of x has a unique solution with x at x naught equal to some y naught y1. So, that is what is given. So, okay, this has unique solution in I, okay. So, So you can also view. So this is actually, there is a more general theorem. So if you have a system like this, if this is true, if this is bounded in a rectangle like this, so you take this x naught, so initial value is x naught, and your this you think of your R2, okay, this is your x, this is your x, and this is your capital X. So you are actually in the space. So at this point you will have some rectangle. So for all in the neighborhood of x naught, so let us say this is your I, x naught is here, so you will have a box containing x naught and that y naught y1, middle point is y naught, so this middle point is actually x naught y naught y1. So because y naught y1 is in x set x, okay. So in this neighborhood, in this box, if these are functions are continuous, you will have a unique solution. So passing through, you will have a space curve in the x, that means you have a yx in the neighborhood of x naught, okay. That is what is the existence theorem. But if you see that there is a global existence, if you see that it is actually continuous, if your function is, it is, I remove this lower upper rectangle, so in this full, okay, for every x naught belongs to I, y naught y1, okay, that takes all the values. Let us take whatever all the vectors here in this direction, okay. If in that, if this is true, that is actually true, okay, because there are only functions which are only depending on this x variable, so they are all bounded. So in that case you will have a global solution, not only the neighborhood, so it will be, you will have a full up to here wherever it is defined, okay, in the full I. So that is what is the existence uniqueness theorem. You will have a unique solution, you have a solution, it is actually unique, okay. So you can assume that without proof, kind of justification is, this is what you will see in the textbooks, where if you are interested, you can get into some reference books, you can see that existence theorem, you might see this form, so that is same as this form, okay. So with this I will give you property number 2. So property 2 is, if you are given the homogeneous second order linear homogeneous equation, that is let y1 and y2 be two solutions of y double dash plus px y dash plus qx y equal to 0, where x belongs to I, okay. If here is given, when do I know that they are linearly independent? So y1x and y2x are linearly independent if and only if I will have some expressions to be satisfied by these functions y1 and by these solutions y1 and y2, that is y1 y2 dash minus y2 y1 dash, which are functions of x, which has to be not equal to 0 for every x in I. So this is what is the property number 2. So you can say if you are given two solutions which you don't know how to find, but if you are having two such solutions, you can say whether they are linearly independent or not. They are linearly independent if you can check this condition, okay. So this is equivalent to, you can equivalently put it in this way. So if you know the logic, A implies B, contrapositive is not B implies not A. So you can put it in that form. So if I write, if I use that logic, if these are equivalent, these two statements are equivalent, keeping this in mind, you can rewrite that property as y1 and y2 are linearly, y and y2 are linearly dependent if and only if y1 y2 dash minus y2 y1 dash equal to 0 for every x in I, okay. You can do like this. So for some x naught belongs to I, right. So if this is not true, that means there exists some x naught. If this is not true, there exists some x naught that is true, implies they are linearly dependent. If they are linearly dependent, So that means you are going from here to here. So if they are linearly independent, the not of this is there exists some x naught that belongs to I such that this quantity is 0. So we will prove this statement. So in a straightforward way, if we rewrite like this we can prove nicely. Okay. So start with they are linearly dependent. So what do you mean by, so we will go from this side. Okay. So we will prove from this side, assuming that y1 y2 are linearly dependent, then we will show that this quantity is 0 at some point. Okay. So the linearly dependent means they are actually parallel. That means y1 by y2 is a constant. Okay. So let's call this some c. That implies y1 minus c y2 equal to 0. Okay. So you can differentiate this because this y1 y2 are satisfying second order equations. So if you differentiate y1 dash minus c is a constant, y2 dash is also 0. This is true for every x. Okay. This is true for every x. So this means, this together means, this is by differentiating the first this equation, you can get this equation. So this, if you can write it as a matrix, y1 y2 y1 dash y2 dash a matrix and 1 minus c equal to 0 0. So I know that c is a constant and they are dependent means, and once they are linearly dependent, you are given that they are non-zero solutions, two non-zero solutions. Okay, you can take it as two non-zero solutions. If there are two non-zero solutions, this constant should be non-zero. Okay, so this constant should be non-zero. So you have 1 minus c, like that you have a non-zero solution for a system Ax equal to 0. So when do you have a non-zero solution for this system? That means the determinant A has to be 0. Okay, when x is non-zero, satisfying this implies non-zero. So that implies modulus of A has to be 0. That means here, what is the modulus of y1 y2 y1 dash y2 dash equal to 0 for every x? That means this is exactly your condition, y1 y2 dash minus y2 y1 dash equal to 0 for every x. So you only need at some point, so you can take some x naught. Okay, so that means this is proved. So if this is dependent, I proved this one. That is straightforward. Okay. So let's prove the other way, that if I assume that the condition is true. Okay, if I assume y1 y2 dash minus y2 y1 dash equal to 0 for some, okay, for some x naught belongs to I, then I want to show that they are linearly dependent. So what you do is you consider the same system. So whatever you have y1, but you consider at those values. Okay, y1 at x naught, y2 at x naught. This system you consider. Okay, so y1 dash at x naught, y2 dash at x naught. This matrix into some c1 and c2, some constants. You take it. You don't know this. Okay, so you consider this system. So you have you consider Ax equal to 0, where A is given like this with these values, where y1 y2 had the values y1 and y2 and its derivatives at the point at x naught. Okay, for which this quantity is 0. So you consider this system, and you know that this determinant is 0. So you know that this determinant is 0. That is what is given. Implies if the determinant of A is 0, implies I will have a non-zero solution. Okay, there exists non-zero x naught such that Ax equal to 0. So you have a non-zero solution for C1 and C2. So that implies there exists C1 C2 matrix vector non-zero. Okay, so you will get such a non-zero solution. Okay, now we consider some phi x, which is you make a C1 with y1x, with these constants. So let us assume that both are non-zero. Okay, you will see that both of them has to be non-zero. One cannot be 0 and one. So certainly this is non-zero means one of them is non-zero. You will see that both of them are actually non-zero. Okay, so whether they are 0 or not, one of them or both of them, whether you know whether one of them is 0 or not, With this you know that there exists some C1 and C2 vector which are non-zero. As a vector it is non-zero. That means it can be one of them can be 0. Such a C1 C2 you form some function phi like this C1 y1x plus C2 y2x, because y1 and y2 are solutions of the homogeneous equation. So what happens? This satisfies, once you form this satisfies the equation, the equation ODE. The ODE is y double dash plus px y dash plus qxy equal to 0. And what are its values at x naught? Phi at x naught is C1 y1 at x naught, okay, plus C2 y2 at x naught. What is its value? This is simply you multiply this vector with this, that is y1 C1 plus y2 at C2 at x naught, that is 0. Okay, so that is 0. And similarly phi dash at x naught, that is if you actually from phi x is this, phi dash if you calculate C1 at y1 dash at x plus C2 at y2 dash at x, that is the derivative at x. You put x equal to x naught, and then this becomes y2 y1 at x naught. Okay. And this is again the second element, y1 dash into C1 plus y2 dash C2 is also 0. Okay. Now from the uniqueness, because p, q are continuous functions, and you know that if you take this, so with this phi satisfying this equation, and these are the initial conditions, phi at x and phi dash at x naught is 0 0. Okay. So that you have such a solution C1 y1 plus C2 y2. Okay. And you know that 0 is also satisfying, y of x equal to completely 0 for every x in I also satisfies the equation and the initial values. Y at x naught is 0, y dash at x naught is also 0, because you simply differentiate yx equal to 0, you get that. Okay. So I have two such functions, phi is also satisfying the initial value problem and 0 is also satisfying the initial, by the uniqueness of the solution for such a for the differential equation with the initial condition. Okay. By the uniqueness of the initial value problem, this phi x should be equal to 0. So what is phi x? C1 y1 of x plus C2 y2 x should be equal to 0. So that means I can write y1 x equal to minus C2 by C1, okay, into y2 x. That implies y1 by y2 equal to minus C2 by C1. So this is not a constant. Okay. Assume that C2 is 0. If C2 is 0, so okay, so we have seen that this is non-zero. This as a vector this is non-zero. Okay. So if C2 is 0 and C1 is non-zero, then C1 into y1, because y1 is a non-zero function, C1 has to be 0. So both, that is not true. Okay. If C2 is 0, C1 is also 0 by from this. Okay. If assume that, see, you have got some C1 and C2 satisfying this, you are working with those C1 and C2. Assume that C2 is 0, then my C2 will be 0 here, then C1 y1 is 0, that means C1 also will be 0. Okay. C1 is 0 because y1 is non-zero solution. So both, if C2 is 0, C1 is also 0. So that means both C1 and C2 should not be 0 if you want this vector C1 C2 which is non-zero. Okay. So that means C1 C2 both are non-zero, that means that their the ratio is also non-zero. So this is exactly constant, right? This is exactly constant, is a constant. That implies this is exactly the definition of y1 y2 are linearly dependent, they are parallel to each other. Okay. That is how you show. So if you are given a two linearly independent solutions, two non-zero solutions of the homogeneous equation, they are linearly independent if and only if this condition is satisfied. This condition is non-zero for every values of x. That is equivalently we are putting in this way, and then we show nicely very easily just by considering a small system, we can show that they are dependent if and only if that quantity is 0 at some point x naught. Okay. So this naturally, so we can define naturally. So there is a definition. So this quantity, whatever you see the right hand side, that quantity, we can define it as a Wronskian. This is the Wronskian of Wronskian of two functions. Okay, Wronskian of, so if y1x, y2x are two functions defined on I, which is in R. Okay, then Wronskian of y1, y2 of x is defined as the determinant, that is y1x, y2x, and y1 dash x and y2 dash x. So this is your y2. This determinant is nothing but your quantity. So y1 y2 dash minus y1 dash y2, or y2 y1 dash. So this is exactly, this is called Wronskian. This is the definition of Wronskian. So if you are given, if these are, see, you can note that these are two functions. I define this Wronskian like this for every x in I. Okay, so these are only two functions. They are not solutions of the linear homogeneous equation. If they are if they are solutions of the linear second order homogeneous equation, then they are linearly independent if and only if this Wronskian should not be 0 at every point. Okay, so but this is not true for general functions. You can consider some example I give you. So 1 log x, I consider these two. Okay, so what is the Wronskian? Wronskian of these two functions. So Wronskian of 1 log x or x log x. If you think of x log x, let me see. Okay, and we will define the domain later. So this is simply x log x 1 by x. Okay, so what is the determinant? 1 minus log x. So you can see this. You know that x log x, if you actually plot x log x is y equal to x is this. Okay, y equal to x, y equal to log x is some other thing, right? Goes like this, right? Simply define only between open interval 0 to 1, 0 to 2, let us say. You see that these two functions are clearly linearly independent, but they are not the solutions of any differential equation, right? Because a Wronskian can be 0. Wronskian is this, a Wronskian at x equal to 1. Okay, Wronskian of x log x of, so function of x at 1, this is 0. Okay, Wronskian is 0. Wronskian is 0 implies Wronskian is at some point it is 0, right? So at 1 it is 0. So implies they have to be linearly dependent. That means they have to parallel to each other, but that is not the case. That is true. That means if you want that Wronskian, once the Wronskian is 0 at some point, then the functions y1 and y2 are linearly dependent only if they are the solutions of. That is true only if that is true only when these are the solutions of second order linear homogeneous equation. Okay, not for the general functions. This is the example. Okay, so this, if you consider these two, and though the Wronskian is 0, they are not actually linearly dependent. Okay, so we will have a property 3 in the next video that tells you that if Wronskian of x naught at Wronskian at some point is 0 or non-zero, okay, then Wronskian at x at every point is 0 or non-zero every point. Okay, so this is done by deriving a formula called Abel's formula. Okay, so next class we derive Abel's formula, and then we see this property 3. So once the Wronskian is 0, and the Wronskian is 0 everywhere. Once the Wronskian is non-zero at some point, then the Wronskian should be non-zero at every other point. This is proved by looking at a formula called Abel's formula. We will see in the next video.